Good afternoon, my name's Alex, and today I'll be presenting my MATH1307 forecasting major project presentation, which is forecasting Essendon mean home attendance for the years 2020 to 2029 inclusive. So the project overview, data was obtained from afltables.com, which provides freely available information relating to the Australian Football League. So the dependent variable is the mean home attendance figures for the Essendon Football Club for the years 1921 to 2019 inclusive. So home attendance is for games that Essendon were the designated home team. Independent variable is proportion of games won for the Essendon Football Club for the same time periods. It's worth noting the data is incomplete. Its crowd numbers are only recorded from 1921 onward, despite Essendon being part of the VFL AFL from 1897 onward, but there's still an adequate sample for conducting an analysis. So the aim is to conduct an appropriate descriptive analysis, then fit models, and select a best model for forecasting the next 10 years. So we're using two modelling techniques in this project: distributed lag models, which make use of the independent variable. There's a number of different approaches to DLMs, and we'll be using a number in this project. Will be explained a bit more further on. And state space or ETS models, which extend exponential smoothing methods and are able to produce prediction intervals compared to the simple point forecast if you just were to stick with exponential smoothing methods. They do not make use of the independent variable. Some model selection criteria. So models will be selected based on the mean absolute scale error, or MACE, on the test data. MACE values are greater than 1 indicate worse forecasts in terms of mean absolute error than a naive model forecast. So it's kind of a good yardstick when you're looking at the MACE values. Additionally, we'll look at residual analysis, as accurate models that do not meet key assumptions are not useful, and other things such as fitted value comparison will be used if necessary to decide between better models, and of course the principle of parsimony would be adhered to in model selection. So here's the time series plot of the dependent variable. So as you can see, there's some autoregressive movement average behaviour, there's no seasonality, there's a period of large variance during the 90s because of the intervention point when the VFL swapped to the AFL and the mean home attendance figures really shot up. So the ACF plot shows that there clearly is autoregressive behaviour as all lags are significant, and we can't see any seasonality here. So to help control that variance that we saw in this plot, which is quite high at one period but low at the start, used a Box-Cox transformation which produced this transform series with a more controlled variance. So this series was used as an input to all the models rather than the raw series. And here's a time series plot of the dependent variable in green and independent variable in orange. So as you can see from this plot, it doesn't seem like there's a particularly strong relationship between the two variables, but we'll leave it up to the models to determine whether or not the proportion of wins for Essendon is actually useful in predicting mean home attendance. So distributed lag models, so there's finite models which use a finite number of the independent variable lags, and this is denoted with the letter Q. The Coik model, which uses a transformation to make the model kind of mathematically possible, and autoregressive distributed lag model, which uses lags of the independent variable at the finite model, but also lags of the dependent variable, which is denoted by the letter P. So in this model, we tested Q 1 through 10 for the finite models, and then Q 1 through 10 matched with P 1 through 10 for the autoregressive models. That's not necessarily a limitation of the models. You can try different combinations of P and Q, but just for simplicity in this project, they were just matched up through 10. So here you can see the finite models MACE, which are all quite bad, all over 9, all well above 1, indicating they're not particularly useful. The Coik model is much better MACE, but it's still above 1, indicating it's not a particularly good model. And then the cells highlighted in green show for the autoregressive model there were two models that produce MACE values below 1, so the Q equals 2, P equals 2, and the Q equals 6, P equals 6. So 0.81 for the larger model versus 0.87. So I had a look at the residuals for those models. So you see for P equals 2, Q equals 2, and larger model. So both of them have approximately normal histograms, somewhat random time series plots that are almost white noise and no significant lags in the ACF. So I ended up selecting the P equals 2, Q equals 2 model to go forward as a candidate model, given that it has MACE, which is not too much higher than the larger model and very similar residuals, but also has a lot less parameters. It's much more simple, given it's only got 2 lags of each. So then going into the state space models, tried all mathematically possible models without seasonality, as there's clearly no seasonality. And there's the models tested. Parameters were optimized on mean absolute error rather than likelihood, which is the default. The parameters were restricted to the admissible range, which means they're not bound between 0 and 1, which is can be typical in this type of modelling. And this is the results in terms of MACE. So again, they're all above 1, some of them not too far above 1. So basically, this is where I'm up to in the project at this point. I'm going to take the Q equals 2, P equals 2 autoregressive distributed lag model forward, look into it a bit more, and produce forecasts for the next 10 years. Thank you.